So today's lecture, the topic is going to be balls and bins, which is a very nice and convenient abstraction for many problems in the analysis of randomized algorithms. So balls and bins. So the idea is that there are n bins, and we toss m balls into these n bins. Each ball goes to a uniform at random bin, and we basically perform analyses on how many bins are in how many balls are in various bins, what is the maximum, when does it take to hit all bins, so on and so forth. So today what I'm going to tell you are a collection of what I consider key facts about balls and bins that sort of any student who has done a course in randomized algorithms should know. And often these statements will have applications in various places, and we'll see some of these applications during the course. Some I'll call them sort of key facts. I'll prove them as I go along about balls and bins. And a note that right now I said that each ball goes to a uniform at random bin. So essentially this is equivalent to m draws from the uniform distribution on the set of the first natural numbers. And so you can always phrase everything just in terms of distribution, sampling from this distribution. But the balls and bins it's very convenient to have this mental picture of balls and bins. So let's start with a simple fact that many of you may already know about, known as the birthday paradox, which is not really a paradox in the logical sense, but it's a surprising statement. So the birthday paradox says if you take 30 random people, it is likely, usually with probability at least half, that 2 people have the same birthday. Now, this is considered surprising because, the number of birthdays is essentially 365 or 366 if you include leap years. And so it seems that you need very few people to actually get the same birthday twice, despite the fact that, somehow, if you would think about it deterministically, you would have to see at least 366 people before you saw the same birthday twice. But when you take people randomly, this number shrinks dramatically. This fact is going to be something that will. So I'm going to sort of be revisiting this fact multiple times. So for now, I'm going to just prove the basic version. So the way to think of this in terms of balls and bins is that a ball is a person and a bin is a birthday. So when you draw, intuitively you draw a random person, it's like taking a ball and putting it into a random bin, which is a birthday. Alright, does this make sense? So you're basically, when you're drawing from, in some sense, the uniform distribution on birthdays, we think of it as each draw as a person, and this person, has a particular birthday. So you get a ball, you ask them, what's your birthday? And you toss them into that bin. And so another way of thinking of this, really in terms of balls and bins, is we do, m tosses or m ball tosses. What is the probability? What is the probability that some bin has 2 balls, or at least 2 balls? Because this would imply that you had 2 different people with the same birthday. Or generally phrased alternately, how large should M be so that some bin has at least 2 balls? And this is really with high probability because we're making randomized statements here. Okay, so it's actually fairly easy to analyze the event. But what is I think surprising and what will be of significant utility for us is the actual bound on M that we get. Okay, so let's consider the complement event. Which is you throw M balls, no bin has more than 2 balls. Equivalently, all bins have less than equal to 1 ball. Right? So this is the event, the complement event that we're considering. So let me break this up into the event EI, which is the ith ball goes into a distinct bin. Right? And this is what I'm interested in. The ith ball goes into a distinct bin. The event that I'm interested in is the probability of the intersection of I going from 1 to M. Now, sort of very similar to Kargar's analysis of the min-cut algorithm, we can just break this up into the product I going from 1 to M using conditional probabilities, and we could say that this is the probability of the ith event conditioned on all the previous events happening. So this would be j less than I of the event aj. Okay, and just writing this out in English, I'll say this is the probability that the ith ball goes in a distinct bin conditioned on the first I minus 1 balls in distinct bins. Right? So this is the probability of my event. So this is the probability, this is the event that all bins have at most 1 ball. And I've broken this event into this product, right, of the product of conditional events. The probability that the ith ball goes in a distinct bin conditioned on the first I minus 1 balls being in distinct bins. Okay? Any questions? Is this clear? All right. Now let's look at, this product. Let's look at each individual event. And this was the probability of the ith ball going into a distinct bin conditioned on that. And this turns out to be fairly easy to analyze, because what we're saying is, so here are the n bins. These are the n bins. at this stage, just before the ith draw, the first I minus 1 balls are in distinct bins. So how many bins are occupied at this stage? How many bins are occupied before we dropped the ith ball? I minus 1, right? So there are I minus 1 bins that are occupied. So there are I minus 1 of these. And what we need is for the ith ball to go into a different bin. So the probability that the ith ball avoids one of these is exactly n minus I minus 1 divided by n, which I will write as 1 minus I minus 1 divided by n. And so the probability that all bins have at most one ball is simply the product of this. So it's I going from 1 to m of that. This, we can use the Taylor approximation of 1 minus x being at most e to the minus x, and just say this is at most the product of I going from 1 to m of e to the minus I minus 1 divided by n. So I'll write this as e to the minus sum of I minus 1, I going from 1 to n of I minus 1 divided by n. Okay. And this we get, just by writing things out, we'll get this is m times m minus 1 divided by 2n. Okay, this is m times m minus 1 divided by 2n. All right, so far so good. Any questions at this point? Any questions? So everything is clear. And so what does one get over here? So sorry, I'll just quick reference to something that I have here. And so now the question is, if m is, let's say, at least I mean, we can actually put this in exactly. We'll say root 2 the natural log of 2 plus 1, just that. Then this probability is at most a half. Indeed, if m is k times n plus 1, so think of k being a constant larger than 1, then the probability is at most e to the minus k squared divided by 2. Right, so what we get here is that the probability essentially decreases exponentially in k. I'm sorry, this should be k times square root n. And so the magic number is basically m is theta of root n, or I should say that maybe I should write this out separately. When m is much larger than root n, the probability of 2 balls landing in the same bin is overwhelmingly high. was overwhelmingly close to 1. And indeed, the converse is also true, that if m is much, much smaller than root n, then with high probability, all bins have at most one ball. So one has to turn this inequality in the opposite direction, for which you can use this approximation. You just say this is E. You take sort of a second degree Taylor approximation, E to the minus x squared for all x less than half. And if you plug this in over here and you go through the analysis, you will pretty much get the same term with a different lower order term. And this I will leave as an exercise. So prove this fact. Prove this fact as an exercise. And so the punchline is, essentially theta of root n, m equals theta of root n suffices to get a what's called collision. Collision, which is two balls in the same bin. Okay? So we will revisit this with a more sophisticated analysis later, but hopefully this is clear. If there are any questions, please ask right now. So is this clear? Right, so it's likely that many of you have seen this analysis before, and I think the key is the order of m is its root n, which is much smaller than the universe size. So you have n bins, but if you throw root n balls, you are likely to get a collision. And indeed, it's sort of as the multiple of root n increases, as m becomes a larger multiple of root n, the probability sort of goes, or rather the probability of not happening goes exponentially to 0. Okay, any questions about that? All right, if not, let me do another fact, another well-known fact and an important one. So there's birthday paradox. There's another that's called coupon collector. Now it's usually phrased in terms of collecting a bunch of coupons, but you can also phrase it in terms of balls and bins, which is how large should m be so that all bins have at least one ball, or this is basically all bins are non-empty. So how large does m need to be so that all bins have at least one ball? Now the actual bound and the proof are slick, which I don't like, because slick proofs often don't give you a lot of intuition. So let's sort of get intuition first. And even if you already have seen the answer and you know the answer, I think it's always useful to have a quick and dirty mechanism to get a bound, and then you can do sort of more careful analyses to prove the bound formally. So consider a bin. Fix any bin. The number of balls in the bin, is distributed is distributed as B, it's a binomial where you're doing m draws and the heads probability is 1 over n. So what is the probability? What is the probability that the bin is empty? No, what is the probability? Okay, can someone, what is the probability that the bin is empty?
1 over n to the m. Sorry, n minus 1 over n
To the n.
to the m.
So it's, or 1 minus 1 over n to the m. Right? And using this approximation, which we will use very heavily, is approximately this is e to the minus m divided by n. Okay. Now that we have this probability, we can ask what is the expected number of empty bins. Okay, what is the expected number of empty bins? So let me write, let me say the random variable xi is the indicator, for the ith bin being empty. What we just argued was the expectation of xi, because this is an indicator, this is just the probability that xi is equal to 1. This probability is approximately e to the minus m over n. What we're interested in is the expectation of I going, the sum of xi, I going from 1 to n. And so this is approximately n e to the minus m divided by n. Okay? Question now is, at what value, again approximately, right? At what value of m is the expectation going to be less than 1? So how large does m need to be so that the expected number of bins goes less than 1? So what do you need m to be? Yeah, so what's the magic value? Should be n log n.
n log 1 over n.
Not log 1 over, but log n, right? Because if you said m to be n log n, then e to the minus m over n is going to be 1 over n, and so n times that is going to be n over n, which is 1. So it seems like the right answer is n log n. And indeed, this quick and dirty analysis is basically the truth. The true answer is n log n with with a lower order error term. And so now let me prove that formally. So the theorem is the expected value of m at which there are no empty bins, right? So hopefully this is the expected value of the first m at which there are no empty bins. This is actually equal to n times the nth harmonic number, which is essentially n log n plus theta of n, right? So it's n log n with a lower order term. Now the proof, which actually nails down the expectation exactly, is surprising. It's a very slick proof. So let's define the random variable. Well, let me not use x because I used x over here. So I'll say let yi be the number of balls required to go from I minus 1 empty bins to, I should say, I'm sorry, non-empty bins, I minus 1 non-empty bins to I non-empty bins. Okay, so here's how I'm thinking about this, right? So here's all the draws that I'm doing. This is my final M. These are all the draws. So think of this as draws or balls. Like, think of these are the balls that you're dropping. So initially you're going to start. Initially there are n non-empty bins. So as soon as you do the first draw, so let's just say this is 0. As soon as you do the first draw, how many non-empty bins are there? So let me write so here I have draws, and above I'm going to write the non-empty bins. Right, the non-empty bins goes from 0 to 1. Now we are looking at the M where the non-empty bins becomes n. And then you do another draw, and then it's going to become 2. Note that this is a random process. Now eventually as you go along, you're going to have to do more draws, or you have to drop more balls to get another non-empty bin. So initially it's probably going to be pretty quick, but then at some point this is going to become longer and longer. So at some point, to go from I minus 1, you're going to have to do lots of ball drops to go up to I. And this I'm going to refer to as the random variable xi. So I have broken up M, which is, you can think of as the time or the number of ball drops, so that all the bins are non-empty, into the sections where the first bin is non-empty, then I have 2 non-empty bins, then 3 non-empty bins, so on and so forth. Note that this is not keeping track of the index of the bin. This is keeping track of the number of bins. I'm not saying that at this point the bins labeled 1 to I minus 1 are non-empty. No, I'm just saying there are I minus 1 non-empty bins, and then I want to get to I non-empty bins. So I break up my M into this sum. So this is going to be x3, this is x2.
Did you mean to write y?
I'm sorry, y. My apologies, y. It's y. I'm sorry, y. So the random variable that I'm looking at, which is really M, can be expressed as the sum of I going from 1 to n of yi. Okay, this is sort of the key trick to break up the total number of balls that have been dropped into sort of these intervals, where in this interval you increase the number of non-empty bins exactly by 1. Okay. So now at this point we can now do our usual powerful linearity of expectation step. So I look at the expectation of I going from 1 to n, and I write this out as the summation of I going from 1 to n of the expectation of yi. Okay, fairly simple. Okay, so what is yi? It says, there are I minus 1 empty bins. There are I minus 1 empty bins. Keep tossing balls until a ball goes, I'm sorry, non-empty bins. Non-empty bins. Now, I minus 1 non-empty bins. Keep tossing balls until a ball goes into an empty bin. Right? This is what we're looking at. So, and the random variable yi is the number of tosses. So yi has a name. Yi is a particular kind of random variable. What is it?
It's Poisson.
It's not Poisson.
Geometric?
it is geometric. It's a geometric random variable. Right? Y is a geometric random variable. And what is the parameter? So what is a geometric random variable? Recall, a geometric random variable is the number of coin tosses until we see heads. Right? Number of independent coin tosses until we see heads. So what is the probability that a single ball goes into an empty bin at this stage? It's n minus I minus 1. Yeah, exactly. Right? So yi is distributed as a geometric random variable with n minus I minus 1 divided by n. So why this? This is the probability that a single ball toss goes into an empty bin, because that's the number of empty bins you have. Right? So this is essentially, I'm saying it's distributed geometrically as n minus I plus 1 divided by n. So what is the expectation of a geometric random variable? What is the expectation of a geometric random variable? It's a reciprocal of the probability, so it'll be n divided by n minus I plus 1. Now let's go back to our linearity of expectation. The expected value of the m that we want is the sum of I going from 1 to n of n divided by n minus I plus 1. So just rewriting this is basically a sum. So note that just looking at the bounds of the sum, when it's n, it's just 1 divided, it's the denominator is 1, and when I is equal to 1, the denominator is n, so I can just write this as that, which is exactly n times the harmonic number. Okay, this proof is a work of art. This is incredibly slick. And I think that in some sense, the more you think about it, the more the slickness will grow on you. And that's because what you did was you broke up the total number of draws. You broke up the total number of draws into sort of this careful sum, which is a summation of yi. And each of these becomes easy to analyze. So instead of thinking about it in terms of looking at bin 1 and bin 2 and bin 3, you kind of keep track of how many bins are non-empty at each stage, and you look at how long it takes to go from one to the next. And so you look at the summation of yi, where yi is the number of balls required to go from I minus 1 non-empty bins to I non-empty bins. And then yi is a geometric random variable. It's easy to analyze its parameter. You take the expectation of the geometric random variable, you get the reciprocal of the parameter, and then that's it. And then you just do the algebra and you're done. So you have n times harmonic number. And this proof is it's short, but it's quite non-trivial. To me, sort of the easy calculation is this. Of course, this does not really give you this analysis here, which is the expected number of empty bins. Obviously doesn't give you the same thing as the expected number of ball drops to get to no empty bins. But on the other hand, the calculations give you pretty much the same bound. This is often what many researchers will do, is do a quick and dirty analysis to get some bound and then try to prove that that bound is correct. Okay? Yes.
So here we're showing something about the expectation.
Yes.
In the previous example, we showed something about bounding the probability that a certain thing will happen. When do we care about one versus the other?
That's a good question. In general, what you care about is probably the entire distribution, and often, you know, one of them might be easier to analyze than the other,
Okay.
and it requires, some amount of experience to know which is which. What I'm describing here are sort of the conventional ways in which these bounds are represented. It is also known that there are concentration bounds. That is, that the probability that it deviates more than, there actually there are very detailed. The behavior of this is known very well. So it's known that the probability that that the true bound deviates from this bound by c times n is e to the minus c. So what you have is basically, there's like it's called a sharp threshold. Like, you will have empty bins pretty much precisely at that point. But that's a good question, and those are things, at least for the birthday paradox, we will revisit that and try to understand things about the distribution in finer granularity. I should say that, just conventionally, the reason why this is called coupon collector is it's instead of thinking of balls and bins, you can think of buying coupons, and each coupon is labeled 1 to n, and the question is, how many times do you need to buy before you get all the coupons? Now, I want to sort of go a little bit further down this track, because I think this analysis is also it's also very enlightening in various ways. So I could ask a more subtle question, which is, how large should M be to have, I'll say, at most k empty bins? Right, so I'm just looking at how long do I have to keep tossing balls until I have k empty bins. The coupon collector problem is setting k equals 0. And I'm looking at, just having a general k. And you'll see that this analysis over here is extremely flexible, because you can just take you can take a partial sum of these quantities and you will get it. And so another way of looking at this is, keep tossing until there are n minus k non-empty bins. And this, going back to the analysis above, would simply be looking at the expectation of I going from 1 to n minus k of yi. And again, by linearity of expectation, you have I going from 1 to n minus k of n divided by n minus I plus 1. And so now let's look at the bounds of the summation. So when I is n minus k, when I is n actually I should, I'm sorry, write this out. When I is n minus k, then the denominator is k plus 1. So what we really have is I going from k plus 1 to n of n divided by I. Right? So when k is equal to 0, we recover our original bound. And for general k, we sort of have this partial sum. And you can write this as n, the harmonic number of n, minus the harmonic number of k. Right? And sort of let's just assume that k is going to be at least 1, because we know the analysis for k is equal to 0. So we'll say k is at least 1. So this is really nice, because essentially, ignoring lower order terms, this becomes n, the natural log of n divided by k. Right? And it's actually, it's pretty much exactly this plus theta of n. Right? So this is, so I've nailed this down fairly accurately. And I can work out what the lower order terms are. But for now, I'm just trying to understand, how does this behave with respect to k. So when k is delta times n for some constant, which means that how large does m need to be so that there are at most 1% empty bins, then the expected value is just theta of n, which is linear. So it says that to get a constant fraction of non-empty bins, a tiny constant fraction, it's only linear. So it's the last few bins, that is going from delta n empty to 0 empty, takes almost all the drops, the ball drops. Right, so it's interesting. It's the last portion. There's the small portion towards the end where it's small in terms of the number of bins, but is actually the dominant portion in terms of the number of balls that you need to drop. Additional point that I would like to make here.
To be clear, are you saying for any constant delta between 0 and 1?
Yeah, I'm talking about, yeah, sorry, I should have clarified. My apologies. So I'm thinking of delta being delta, in 0, 1 constant. My apologies. I meant delta being constant. Right? Because when k is delta n, then this is log 1 over delta. Right? And you can plug in the values of delta, you'll get a more nuanced bound over there. But what I want to sort of emphasize here is this slick proof is surprisingly flexible. It tells you a lot. Another point which is sort of interesting is when m is n log n, the expected number of balls in each bin is log n. So which means by the time all bins are non-empty, I'd say, an overwhelming, this is not proven, but this, you can use Chernoff bounds to prove this. An overwhelming fraction of the bins have log n balls. Right? So by the time you actually make all the bins non-empty, there are actually lots of bins that have many balls. So another way of looking at this, which is, this is the part where the probability is somewhat counterintuitive. So after m equal to theta n balls, all bins have expected theta of 1 balls, but a non-trivial fraction are actually empty. A non-trivial fraction of them are empty. So this is, it's an important point to understand. And if there's really any message that I want you to take from the coupon collector analysis, it's this, that, the expected, each bin, you can get these expected bounds. But because there are so many bins, there are n bins, the expectation doesn't capture the entire behavior. There are significant deviations from the expected behavior. When m is theta of n. To get the expected behavior to sort of be representative of the true behavior for each bin, you kind of need the expected number of balls in each bin to be log n. And then at that point, actually Chernoff type concentration will kick in. You can take union bounds, and then you can show that, by that point the expectation kind of is representative of the behavior. And this is also related to the Poisson distribution, which we will talk about towards maybe the end of this lecture. So, any questions about these parts, these two facts that I gave you, the birthday paradox and coupon collector? Okay, if not, let's continue. And I want to tell you about the third fact, which is this is sort of a very intriguing fact. At least the first time you look at it, it's quite surprising. What is the maximum load? So suppose we throw m equal to theta n balls. For now, just think of m being equal to n, for example. What is the largest bin, or what is the size of the largest bin? So we know that the expected, all bins have expected theta of 1 balls. But what is the largest going to look like? To give you a very direct application of this statement, or rather an application of understanding this statement, is consider building hash tables. So hash tables you can really think of in terms of balls and bins, where the bins are the hash values, balls are the elements being stored, and you would recall from your 101 analysis that you need the number of hash values to be typically close to the number of items. Only then do you get expected constant time. So we expect every hash bin to be constant sized. But the largest bin could be super constant. So there's sort of an important point over here, which is, let's say that the bin size, let xi be the size of the ith bin, and again m is theta of n. So it's quite clear that the maximum over I of the expectation of xi, and this is theta of 1, because each xi is identically distributed, right? And each expectation is theta of 1. But what is the expectation of the max? But this could be much larger. Now this has significant implications for memory allocation in a hash table. Let's say that for each hash bin you would like to pre-allocate some memory, so that you would basically then use that memory as you add elements. You need to know sort of what the maximum is going to be so that you can pre-allocate that amount. But if the maximum is going to be much larger than O of 1, then it seems like you're going to allocate much more memory than what you need. So it's tricky, and the behavior here is actually surprisingly nuanced. So let me, before, and again, in this case, instead of sort of stating the theorem and then working out a formal proof, what I'd like to do is to go the opposite way, is just to try to get some intuition as to what is the right sort of right numerology which leads to the bound. And then once you get that, you'll then see that you can apply sort of the appropriate Chernoff bound and get the result. Okay.
In like a lot of hash tables, there's like, instead of having like multiple balls in a single bin, you would like have some scheme that like allows you to redistribute them, right?
Yes, you would need. So this is just looking at maybe the most naive hash table implementation. And actually, you'll see that this analysis already tells you why a direct naive instantiation can be tricky. Yeah. All right. So sorry, I've just run out of paper. So give me a second. I'll get some more paper. Okay. So m is c times n. I want you to think of c as a constant. And if you could even just think of c being 1, but think of it just being as some constant. All right. So we said that the number of balls in a bin is distributed as this binomial m n of 1 over n. And now you're going to see an application of the strong Chernoff bound that I showed. Let's apply the strong Chernoff upper tail. Okay, so what is that? So looking at the probability that x is going to be 1 plus delta times, okay, so times c. Okay, so what is x? So let me write this out as xi. So xi is equal to the number of balls in the ith bin. So somewhat abusing notation. Typically I use xi. I've used xi before for an individual trial. Here xi actually refers to the binomial, right? So xi is distributed as b is this binomial. The expectation of xi is just m divided by n, which is c. And you can even think of c being 1. So what is the probability that xi is more than 1 plus delta times c? Now, applying the stronger bound, you're not actually going to get much out of the e to the minus delta square bound, and that's because we want to set delta to be much larger than 1. So we have this other bound of e to the delta 1 plus delta to the power 1 plus delta to the c. Now, I'm not going to try to optimize constants here, and you can, by doing things, you can actually look at this distribution directly and sort of get sharper constants, but that's not the point. So I'm going to refer to this as r, right? The probability that xi is more than r. Now I can just upper bound this rather naively by just saying that this is 1 plus delta divided by e to the minus 1 plus delta to the c. So what I did was I simply replaced that delta with a 1 plus delta, which I can certainly do just to get an upper bound. Now I can write r is equal to 1 plus delta times c. So let me just plug that in and represent everything in terms of r. So this quantity now becomes r divided by c times e to the power minus r. Okay, what's important is that it's r to the minus r. Now if you recall, there was also a bound that just gave you 2 to the minus r. But I want to do r to the minus r. Okay. Now suppose we chose r. such that the probability that x being greater than r is, let's just say, less than 1 over n squared. Suppose you could choose r. Suppose you chose the r such that this happened, that this is less than 1 over n squared. I should say xi. By the union bound, now you can apply union bound. You can say the probability that the max xi is greater than r. This is equal to the probability of the events. I'm sorry. This would be the probability that the max is at most r is going to be at most n times 1 over n squared. Right? Because again, the probability that the max is r is really the probability, the union I going from 1 to n of these events. Right? And this I can just upper bound by n times 1 over n squared. This will give me 1 over n. So this would be the low probability event. So if I choose r so that this is true, the probability that xi is greater than r is less than 1 over n squared, then I know that with high probability the maximum load, the maximum xi is also going to be smaller than r. So what should r be? Again, just writing this out, let's say that I want this to be less than 1 over n squared. Let me take logs. And I manipulate these things around, and you'll see that, r log r plus some theta of r has to be at least 2 log n. So what should r be? What should r be? Okay, does r, setting r to log n, does that work? If I set r to log n, will the left hand side be much more than the right hand side?
Big R, I guess. Yeah.
Yes, capital R. If I set capital R to log n, this is going to work. Right?
If R is large.
What do you mean if r is large? I set r to be log n.
Right, okay, yeah, that would work.
So r being log n works. But it's too much, because when I set r to be log n, what I get on the left hand side is log n log n plus whatever theta of log n, and this is clearly more than log n. So this sort of tells you what you need to set r to be. R being log n divided by log n also works. I'm sorry, log n divided by log n. So it's log n divided by log n. So it's better than log n. And indeed, yeah.
I'm confused. Why are you saying that log n is much greater than log n?
Log n,
Like, you just mean, like, if we're not thinking of it asymptotically?
no, asymptotically this is larger, right? Log n times log n is going to be greater than log n.
Yeah. Okay, never mind. I misread it. I agree.
Yeah, so I'm just saying, but you can improve on that by doing log n divided by log n. Right? If you plug this in over here, so I'm just doing this, I'm just doing back of the envelope, and then we can do it more formally.
Can we also improve on that by adding a log n or a log to the top and a log to the bottom? Just have the top be 1 over log and the bottom.
I'm sorry, say that again.
Oh wait, never mind.
So asymptotically speaking, you will set r to be some constant times this. Maybe not c, but some other constant, some constant. R, if you set it to be log n divided by log n, okay, let's sort of work this out. So let's go back and just look at the bound over there. So let's just say I said it's c prime log n divided by c e log n log n, this to the power minus c prime log n divided by log n. Okay. Now let's just say c prime, I set that to be 2ce. Right, so I'm going to be extremely loose with the constants here. I'm not trying to optimize the constant here. So I get, this becomes 2 log n divided by log n to the power minus 2ce log n divided by log n. I probably don't even need the 2. Now this, I can write this entire quantity. So, okay, let me do this on a separate sheet of paper. So I'm sorry. So let me remember, we said the probability that xi being more than r is at most r divided by ce to the power minus r. Okay. Now I'm going to set r to be, I'll just do ce log n divided by log n. Now plugging all of this in, when I plug it in over here, I get log n divided by log n to the power minus ce log n divided by log n. Okay, and just to be careful, let me just make sure that c is greater than 1. So I'm tossing at least n balls in m bins. But you can, if c was some other is constant less than 1, you can still make things work. It just it becomes a little messier. So this I'm going to write as e to the, okay, so let me minus, I'm sorry, e to the log of log n divided by log n times minus ce log n divided by log n. And this gives me e to the minus ce log n plus log n times log n divided by log n. This is minus. Now what you can see is this numerator will cancel out that numerator there, right? And that's going to be the key. This denominator, I'm sorry, the denominator of log n can cancel this out, and then you'll get e to the minus log n. Okay, so just to be formal, if I make that 2ce log n over there, I'll get a factor 2 over there. I can write that log n minus log n asymptotically is going to be at least log n divided by 2. Plugging that in, what I'll get over here is that this is e to the minus ce log n, which is definitely less than 1 over n squared. Okay, so the theorem is that let m be equal to Cn for c being greater than equal to 1, then the probability that the largest bin has more than 2 CE log n over log n balls is at most 1 over n. So what we have is a bound on the maximum load. We have an upper bound on the maximum load. So any questions? Any questions about this? This is, if you haven't seen this before, this is it's a very non-trivial calculation. So let me pause here and take any questions that you may have. Okay, so just to recap, what we have is if m is equal to c times n, so we have put a linear number of balls, and let's just think of c being greater than 1. The probability that the largest bin has more than 2 CE log n over log n balls is at most 1 over n. This is the probability the largest bin has more than log n over log n balls is at most 1 over n. Alternately, we are looking at the random variable max I of xi. This is the largest bin. And we've said the probability that the largest bin is at most 2 CE log n over log n is at least 1 minus 1 over n. So think of, this is a high probability. So I'm just saying we are roughly nailing down, we're getting an upper bound on the largest bin. It turns out that there is also a lower bound, which is pretty much the same. So which means we asymptotically nail down the behavior of the largest bin, in terms of the asymptotics in terms of n. And you can show that the maximum largest bin, the size of the largest bin, is at least some constant. This is going to be some small constant, right? This is potentially like some constant less than 1. The probability that the largest bin is more than some constant times log n divided by log n is actually at least 1 minus little o of 1. I probably don't have time to do the proof of this part, but hopefully over this lecture and maybe over the next lecture I'll give you enough tools that that you should be able to do it yourself. So these are the basic facts that I wanted to tell you about. Given that we've discussed this is also referred to as the max load or the largest bin problem, a very celebrated result that I'd like to tell you about is the power of two choices. So from a hash table perspective, this is bad news because when you build a hash table, if you want to hash m elements, you are going to choose your n, that is this number of bins, to be something like theta of m. And now the problem is your largest bin actually tends to be fairly large, so the memory allocation is a hassle. You don't get really a balanced allocation. So here's a variant you can do. To place a ball, which is also the same as hashing an element. Now we are not going to pick a random bin. We will pick two uniform at random bins. And you could do this using a hash function and put the ball in the smaller bin. So does this make sense? So you pick two bins and you place it in the smaller bin. And there's the celebrated power of two choices theorem by Azar, Broder, Carlin, and Upfal, and this is from 94, says that the maximum load is actually going to have a dramatic improvement to log n divided by log 2 plus O of 1. They really nailed it down. The max load now goes, so previously it was essentially log n divided by log n, but by just picking two choices, it goes down to log n. So it's an exponential improvement. An exponential improvement, and maybe even somewhat more surprisingly, is if we pick D uniform at random bins. Remember now, D is going to be greater than 2. The bound becomes log n divided by log D. So you do not get much of an improvement. So huge improvement, a huge improvement from 1 to 2, 1 bin to 2 bins, but not more beyond that. I should say not much more beyond that. So instead of picking one random bin, if you pick 2 random bins and take the minimum, there's an exponential improvement. But if you pick 3 random bins and then you put it in the minimum, the improvement is only now in the constant factor. So you don't get an asymptotic improvement. So this is referred to as the power of 2 choices, which is to go from 1 choice to 2 choices. There's a huge dramatic improvement, but not much more beyond that. Any questions about this? I mean, I am not, at least as of now, I do not plan on proving this theorem, but towards the end of the course, if there's enough time, maybe I will, or at least sketch out some of the main ideas, because it's such a beautiful statement. A beautiful and surprising statement.
Well, if you're not going to go into it right now, is there any brief intuition for why this?
No, I don't have a good sort of pithy explanation as to why it goes from log n to log n. Essentially, so intuitively, what is happening in the previous analysis is intuitively the number of bins that are actually going to be large are very few in number. And so in some sense, what you can also see is that the very largest bin is probably like a singleton. There's going to be one or some constant number of bins that actually have that many balls. So we can ask, how many bins actually have that many balls? So it's sort of analogous to the coupon collector. Like by the time you collect the coupons, all the bins have log n balls. Now we can say once the maximum hits log n over log n, how many bins actually have log n over log n balls? And it's going to actually be a very small number. It's going to be little o of n. Now, when you do power of 2 choices, the probability that both your choices landed in the large bins is going to be like quadratically smaller. Right? So the probability of sort of increasing the maximum becomes quadratically smaller. Now, it seems, the problem with this intuitive picture is you could say, well, if you took 3 of them, then it's going to be cubic, so it's going to be even smaller. But it turns out that improvement is not going to help you much. So that's sort of about as far as I want to go on that, unfortunately. If I have time towards the end of the course, maybe we'll cover, we can discuss some of the details of this proof. I'm sorry, what doesn't help as much?
Like you only need, it doesn't help us, like choosing 3 doesn't help as much because you only need 1 small bin.
It's a little hard to now phrase that purely in terms of the intuition, because it depends on how the math works out. Right? Because if you do follow this logic, it seems like, there might be a huge improvement because the probability that So essentially, the probability that D choices are all going to land in the large bins is exponentially decaying in D. So you could imagine that increasing D is going to give you huge improvements. But it's sort of subtle in the way that bound sort of enters in the way that it sort of enters the analysis in terms of the max load. So yeah, let's leave it at that. Unfortunately, I don't think there's anything sort of useful I can say beyond that. But what I would like to talk about is so again, the main takeaway from today's lecture is that these three facts: the birthday paradox. So I'll sort of flash those pages in front of you. The first is birthday paradox. When m is essentially is root n, or I should have written this at the end, m being root n suffices to get a collision, which is two balls in the same bin. This is birthday paradox, so you need to know this asymptotics of root n. The second asymptotic statement that you need is coupon collector, which is n log n. You need n log n draws so that there are no empty bins. The third asymptotic statement that I want you to remember is that when m is linear in n, the max load, the largest bin, is essentially log n over log n. Right? These are sort of these fundamental statements about balls and bins. Now, how does one go about proving this statement here, that the maximum load is at least delta times log n over log n? At this point, it's worth taking somewhat of a digression to understand an important technique relating to the Poisson approximation, which comes up. So we write this out as an important tool is the Poisson approximation. So what does the Poisson approximation say? So let's look at m being O of n, which is the situation that we're sort of considering. You could even think of it being n log n, but it's just useful to have a mental picture of m being O of n. So the distribution of balls in a single bin, as we discussed, is this binomial. So the probability that x is equal to k, so the x is going to be the drawn from this distribution. What is the probability that it's going to be k? I can write this out pretty much exactly in terms of so I first decide which of the m draws led to a ball falling into that bin, and so in those which of the there are k draws that led to a ball in the bin. So I get a 1 over n to the k for that, and I get a 1 minus 1 over n to the m minus k for whatever remains. Now, in whatever we're thinking, let's think of k being much, much smaller than m. So I can do some rough approximations, and I get m to the k divided by k factorial n to the k, and e to the minus m minus k divided by n. Right? This is just doing this 1 minus x being approximately e to the minus x, or x being much smaller than 1. Now, because m is much larger than k, I'm just going to write this as m by n to the k divided by k factorial e to the minus m divided by n. This expression over here, which is m by n to the k divided by k factorial e to the minus m divided by n, essentially this is the Poisson distribution. So A good approximation, when k is much smaller than m, and essentially, of course, n is much larger than 1, is the Poisson distribution. So the Poisson distribution, now this is just a discrete distribution, the Poisson distribution with parameter mu is given exactly by this expression, mu to the k divided by k factorial e to the minus mu, and you can verify this is a distribution, and it's an easy exercise. So for all the exercises here, I request the scribe to just write out the proofs of these exercises in the lecture notes. And one way to think of this is really you have m being mu times n, and you're looking at the distribution of m, the limit of this distribution as n goes to infinity. Right? So this is the limit of this distribution as m goes to infinity, fixing m being mu times n. So an important theorem is that sums of independent Poissons is a Poisson with mean being the sum. I should have said that if you have a Poisson distribution, the expectation of x is mu. So it's the Poisson parameter essentially gives you the expectation is mu, which is sort of a very useful fact to have. And the moment generating functions and all of these things can be well approximated, well behaved. Interestingly, the variance of this is also like mu. The Poisson approximation is to say that so right now we have this x1, x2 to xn be the number of balls in the respective bins. So firstly, these are not Poissons. Moreover, they're all dependent, right? x1 to xn are dependent because each of these is coming from the same m draws. So conditioned on one of them, you could potentially affect the other. But consider y1, y2 to yn, where yi is an independent Poisson with parameter m by n. And so the Poisson approximation theorem, there are various versions. Let me give you sort of the most convenient version. This isn't particularly hard to prove. The proof is given in Mitzenmacher and Upfel, but I might not go into the details because I don't think that is specifically relevant for many of the things we'll be talking about. But I think the statement is very, very useful. So it says that let E be an event monotonic in M, meaning that if you increase the number of balls, then let's think of this event as only increasing. So for example, the max load. If you increase the number of balls, then obviously the event is going to remain true. That is monotonic in M, meaning increasing M maintains the event E. Then the probability of this event, look under the random variables x1 to xn. So this is under the normal setting, is at most twice the probability of the event from y1 to yn. Meaning that you can actually just, if you are looking at events that are monotonic and you're trying to prove an upper bound on the event. So this could be like a tail bound for max load or the various things that we've been discussing. If you consider an event that's monotonic, then the probability of the event, if you were to replace each bin by an independent Poisson, is just a factor 2. So you might as well consider things are independent Poissons, which makes the analysis much easier because you have an explicit description of the Poisson. There are lots of tail bounds and lots of specific theorems that you can use for the Poisson. Moreover, these are all independent. So these are dependent. But these are independent. And actually, even if you have an arbitrary event, then you can get a theorem of this form, but instead of a constant, you'll have some dependence on M. And so this theorem, if you apply this theorem, then the proof of this statement actually becomes a lot easier because you could treat each xi as an independent Poisson, and then you can sort of work out the calculations, and you will get exactly this. You will get this out of the Poisson calculations. And so this is sort of an important fact to know, the Poisson approximation theorem, where you can essentially replace the random variable of the number of balls in each of its bin by an independent Poisson. So I'll stop here and take any questions.